You fit a linear model, and it lands almost perfectly on your training data. Then new data arrives, and the predictions swing wildly. The errors explode. Something has gone wrong. Here is a model flexible enough to pass through every single point. On the training data, it is flawless. But look how violently it wiggles between the points. It has stopped learning the trend and started chasing the noise. And there's a fingerprint that gives it away. To bend through all that noise, the model has to crank its coefficients up to enormous, opposing values, plus 400, minus 1000, plus 800. Huge weights fighting each other. That's the signature of overfitting. Correlated or redundant features make this even worse. So we'd love to give the model one gentle instruction. Fit the data, but keep your weight small. That idea is called regularization, and its most famous form is ridge regression. Start where ordinary least squares starts. It picks the weights that make the sum of squared errors as small as possible. For every point, the true y minus the predicted y squared, all added up. Pure fit. Reach changes the goal with one extra term. We keep the fit error, and we add a penalty, lambda, times the sum of the squared weights. This second piece is the L2 penalty. It measures how big the coefficients are. Read the two halves as a tug of war. The fit term wants accuracy. It'll grow the weights to chase every point. The penalty term wants the opposite. It punishes large weights, pulling every coefficient back towards zero. And lambda, out front, is the referee. It sets how hard we push the weights down. The single dial trading fit against shrinkage. Turning that dial is the whole story. So let's turn it. On the left, I'll plot the coefficient path, each weight up the axis, against lambda running left to right. At the far left, lambda is 0. No penalty. So these are just the ordinary least squares weights, sitting up high. Now crank lambda up and watch. Every coefficient slides downward, shrinking steadily towards 0. That is exactly what the penalty does. It squeezes the weight smaller and smaller as lambda grows. But notice, the curves flatten towards 0 without ever quite reaching it. Ridge shrinks the coefficients. It does not switch them off. Hold that thought, it will matter later. And here is what those shrinking weights do to the actual fitted curve on the right. With lambda near 0, the fit is that same wild, overfit wiggle we started with. Big weights, big swings. Turn lambda up, and as the coefficients shrink, the curve calms down. The violent oscillations melt away, and it becomes smooth and gentle, a model that captures the trend instead of the noise. This is regularization working. Push lambda higher still, toward infinity, and the penalty utterly dominates. Every weight is crushed to nearly nothing, and the curve collapses to a flat line. It just predicts the average, ignoring x. That's the other extreme, underfitting. So lambda is a dial to slide along. 0 is plain least squares, maybe overfit. Infinity is a flat, useless line. In between lies the model that generalizes best. There's a second way to see ridge that's just beautiful, living in the space of the coefficients themselves. Put beta 1 on one axis, beta 2 on the other. Every point is one possible pair of weights. Ordinary least squares has one best point, the bottom of its error ball, marked here in blue. Draw the loss as contour rings around it, like a topographic map. The center is the unconstrained least square solution. Now ridge adds its rule. The L2 penalty says the coefficients must stay inside a circle around the origin. Beta 1 squared plus beta 2 squared, no bigger than some budget t. A smaller budget means a tighter circle. Least squares wants the center. But ridge forbids it since it sits outside the circle. The best allowed is the first point where an expanding contour just kisses the circle's edge. That touch point is the ridge solution. Pulled in, its coefficients shrunk. And here is the elegant contrast worth knowing. Lasso, the L1 cousin, swaps this circle for a diamond with sharp corners. A contour is very likely to touch the diamond right at a corner, where one coefficient is exactly 0. That's why lasso can switch features off entirely, while Ridge only shrinks them. The best part, like least squares, Ridge has an exact formula. No searching required. Recall the least squares solution. W equals x transpose x, inverted, times x transpose. Ridge makes one tiny change. Inside the inverse, we add lambda times the identity matrix. That single extra term plus lambda I is the entire difference between least squares and Ridge. And that term earns its keep. When features are correlated, multi-collinear, x transpose x can be singular, its determinant 0. Least squares then blows up. The inverse doesn't exist. Watch what lambda I fixes. Nudge the diagonal up by lambda and the matrix becomes positive definite. Its determinant safely above 0, so the inverse always exists. That plus lambda I doesn't just shrink the weights. It stabilizes the whole problem and cures multicollinearity. Let's grind a real one. Every number by hand. The simplest possible case. One feature, no intercept, and just 2 points. 1 and 2, 2 and 3. First, let's score a specific weight. Take the weight W equals 1.5 with lambda equals 2. The prediction for the first point is 1 times 1.5, so 1.5. For the second, 2 times 1.5, exactly 3. The errors are not 0.5 and 0. So the fit term, the sum of squared errors, is just not 0.25. Tiny, but the penalty is lambda times W squared. 2 times 1.5 squared, which is 2 times 2.25, 4.5. Add them, and the ridge objective is 4.75. See how the penalty dominates. It's pushing us toward a smaller weight. Now the big reveal, the best weight. For one feature, the sums we need are simple. Sum of x times y is 1 times 2 plus 2 times 3, which is 8. Sum of x squared is 1 plus 4, 5. Least squares just divides. 8 over 5 is 1.6. Ridge adds lambda to the bottom. 8 over 5 plus 3, which is 8 over 8, exactly 1. The denominator got bigger, so the weight got smaller. And there it is. The coefficient shrank from 1.6 down to 1. Ridge pulled the weight towards 0, exactly as promised. On noisy, high-dimensional data, that shrinkage is what buys you a model that generalizes. Your turn. Keep that same data set, Ridge weight, equal to 8 over 5 plus lambda. Here's the question. As lambda grows without bound toward infinity, what happens to the weight? Pause, think it through, and predict what the model ends up doing. I'll wait. Let's just watch it happen. At lambda equals 5, the weight is 8 over 10, not 0.8. At 95, 8 over 100, down to 0.08. At a million, it's essentially 0. The denominator races off to infinity, while the top stays fixed at 8. So the weight is driven straight to 0. And a weight of 0 means no slope at all. With every coefficient gone, all the model can output is the intercept. It predicts the same constant for everyone. If you set the weights shrink to 0 and the model collapses to the mean, you've understood what lambda does. Trap 1, the classic mix-up. Ridge, with its L2 penalty, shrinks coefficients towards 0 but never exactly to 0. If you need genuine zeros, features switched off. That's lasso, with L1. Ridge shrinks, lasso selects, trap 2, and it bites in practice. The penalty squares the weights, so it's scale sensitive. A feature in meters and one in millimeters get punished completely differently. Always standardize your features first, so the penalty treats them fairly. Trap 3. Leave the intercept alone. We shrink the slope weights, but the intercept just sets the baseline height. Penalizing it would drag the whole line down for no reason. So it's left out of the penalty. And trap 4. Regularization is a trade-off, not a free win. Turning lambda up lowers variance, but raises bias. You're buying stability with a little accuracy. So choose lambda by cross-validation, not by eye. Let's tie it all together with the picture that names the payoff. Along the bottom, lambda from small on the left to large on the right. Up the side, the test error. How well the model does on data it never saw. With lambda too small, the model overfits. High variance, high test error on the left. With lambda too large, it underfits too much bias. High test error again on the right. In between, the error dips to a minimum. That valley is the sweet spot. You find that valley by cross-validation, trying a range of lambdas and keeping the one with the lowest error on held-out data. Never pick it by eye. So the whole lesson on a page. Ridge adds an L2 penalty to the least squares loss. Fit error plus lambda times the sum of squared weights. It has an exact solution. X transpose X plus lambda I inverted times X transpose Y, and that plus lambda I keeps the matrix invertible even when features are collinear. Lambda is the dial between two extremes. 0 gives you plain least squares, and infinity crushes every weight to 0, leaving only the mean. And hold the essentials. Ridge shrinks the coefficients towards 0 without ever zeroing them, and as lambda rises, it trades a little bias for far less variance. Master that trade, and overfitting loses its grip.